1 minute ago, fishermen in the Bay of Naples pulled their nets from waters that felt unnaturally warm. The sea itself appears to be heating from below. Beneath their boats lies Campi Flegrei, a 13-kilometer-wide volcanic caldera where nearly 3 million people live, work, and sleep directly above a restless giant that hasn't stopped breathing since its last eruption in 1538. In scattered patches across the bay, observers have noted what could be localized thermal anomalies, raising questions about heat flow from the caldera floor. Steam rises from certain shorelines at dawn, and the ground beneath the city of Pozzuoli has lifted 140 centimeters since 2005, accelerating to 3 centimeters per month by March 2025. Is this the prelude to Europe's next volcanic catastrophe? What force is turning the Mediterranean into a cauldron? And why can't anyone predict what comes next? The Campi Flegrei caldera sprawls across the western outskirts of Naples. Its boundaries are invisible to most residents. No towering volcanic cone dominates the skyline. Instead, the caldera hides beneath neighborhoods, ancient Roman ruins, busy harbors, and the very streets where children walk to school. The depression stretches from Pozzuoli to the Tyrrhenian Sea, encompassing 24 craters and volcanic structures that have formed over millennia. More than 500,000 people live directly within the red zone, the area designated for immediate evacuation in case of eruption. Beyond that, the greater Naples metropolitan region holds nearly 3 million residents, all within reach of the caldera's influence. The Istituto Nazionale di Geofisica e Volcanologia monitors every tremor, every gas release, every millimeter of ground movement. But the volcano's true extent remains partially submerged beneath the bay itself, making it one of the most densely populated volcanic hazard zones on Earth. But this is not just any volcano. Campi Flegrei has produced 2 of the largest eruptions in European history. The Campanian ignimbrite eruption 39,000 years ago ejected between 181 and 265 cubic kilometers of material, reaching a volcanic explosivity index of 7. Ash from that blast blanketed the Mediterranean and beyond, altering the climate across the continent. The ground collapsed inward as the magma chamber emptied, creating the vast caldera that exists today. A second major eruption approximately 12,000 years ago, known as the Neapolitan Yellow Tuff event, reshaped the landscape again, depositing thick layers of volcanic material across the region. Since then, at least 70 smaller eruptions have punctured the caldera floor. The most recent occurred in 1538, when Monte Nuovo burst into existence over 8 days of explosive activity. Historical accounts describe fractures opening in the ground, cold water gushing forth followed by hot groundwater, and vapor-charged white clouds rising into the sky. The eruption killed 24 people and created a 100-meter-high cinder cone that still stands today. The volcano has not erupted since, but it has never truly rested. What came next shocked even the scientists. Fishermen avoid certain areas of the bay now. Local captains mark their charts with zones where the water feels warmer, where bubbles rise from the seafloor, where the catch has changed. These observations, while anecdotal, align with a pattern of increased volcanic degassing documented by monitoring networks. In 2022, portions of Lake Avernus inside the caldera turned red from massive algae blooms, an event residents connected to warmer water temperatures. Similar discoloration appeared in stretches of the Gulf of Pozzuoli. While the National Institute of Geophysics and Volcanology has not confirmed a direct causal link between algae blooms and volcanic heat flow, the suspicion voiced by some observers is that intensified geothermal activity at the seafloor could be feeding the phenomenon. The timing of these events corresponds with accelerating seismicity and ground uplift, suggesting a connection worth monitoring. And the signs were already spreading. Ground deformation at Campi Flegrei follows a pattern known as bradycism, slow vertical movement that can lift or lower the land by meters over months or years. Since 2005, the central part of the caldera near Rione Terra in Pozzuoli has risen 140 centimeters, measured by GPS stations that track every millimeter of change. For much of that time, the uplift rate held steady at around 1 centimeter per month. But since late 2024, the pace has quickened. By February 2025, rates reached 1.5 centimeters per month. By March, some stations recorded 3 centimeters per month, the fastest sustained uplift in decades. The ground is rising faster now than during the last major crisis in 1982 to 1984, when the land surged approximately 1.7 meters and thousands of people were evacuated. Streets crack open, buildings develop new fissures. The harbor at Pozzuoli, once deep enough for large vessels, has silted up as the seafloor rises. Each surge brings anxiety. Each pause brings fragile hope. But the ground had one more secret. Since early 2021, seismologists have detected a new type of seismic sequence. These events occur in rapid bursts, with inter-event times so short that individual tremors blur together on seismograms. Researchers call them burst-like swarms. Between 2021 and 2024, these swarms became more frequent and intense, concentrated in the Solfatara Pisciarelli hydrothermal field at the Caldera's center. In May 2024, a swarm of approximately 150 earthquakes struck within hours, culminating in a magnitude 4.4 event, the largest recorded since the current unrest began in 2005. Another magnitude 4.4 quake followed in March 2025, causing minor building damage and 1 injury in Naples. The swarms cluster around a geodetic anomaly, a zone that uplifts less rapidly than its surroundings, despite being located near the area of maximum ground deformation. This anomaly appeared in 2021 and has persisted ever since. Studies published in Nature Communications in February 2025 identified these burst-like swarms as potential indicators of critical changes in the hydrothermal system. In other volcanic contexts, similar seismicity has preceded phreatic explosions. The most dangerous zone lies at Pisciarelli. Fumaroles here release superheated steam and gases at temperatures exceeding 140 degrees Celsius, the highest ever recorded in the caldera's modern monitoring history. Carbon dioxide emissions from the Solfatara Pisciarelli area have surged to between 4,000 and 5,000 tons per day, more than double the levels measured in 2018. The ground is fractured and unstable. New vents open with little warning, sometimes overnight, releasing jets of steam that reach several meters into the air. Drone surveys map the thermal field regularly, revealing hotspots spreading outward from the main fumarolic zone. Some areas are too hot to approach on foot. The risk is not from lava. The risk is from phreatic explosions, violent steam-driven blasts that occur when superheated water flashes to vapor. These explosions can fragment rock, hurl debris hundreds of meters, and trigger mud flows that race down slopes toward populated areas. Phreatic eruptions at other volcanoes have killed scientists and tourists with almost no warning. At Campi Flegrei, the most recent phreatic event occurred in 1198 at Solfatara crater. The next one could happen tomorrow, or it could wait years. No one can say. And fresh trauma was everywhere. In Pozzuoli, residents wake each morning to check the walls of their homes for new cracks. Some outer walls radiate unusual warmth, uncomfortable to touch. Yellow-white mineral deposits creep upward from baseboards in buildings near the most active fumarolic areas, leaving crusty streaks across plaster. The smell is sharp and metallic, especially after rain, when gases push harder through fissures in the foundation. Repairs cost thousands of euros, money spent sealing cracks that often reopen. Insurance companies refuse to cover volcanic damage in many cases. Property values have collapsed in the most affected zones, leaving some residents with few options. "We watch from the balcony as steam curls up in the street," one resident said, "and every morning we check if the paint is blistering." Neighbors have left, but others stay, either unable to afford relocation or unwilling to abandon homes their families have occupied for generations. What scientists discovered changed everything. For decades, the prevailing theory held that ground uplift and seismicity at Campi Flegrei resulted from magma rising toward the surface. But research published in Science Advances in May 2025 challenged that assumption. A team from Stanford University and the University of Naples analyzed 2 distinct periods of unrest, 1982 to 1984 and 2011 to 2024, comparing subsurface imaging, earthquake patterns, and ground deformation data. They found no clear evidence of shallow magma accumulation. Instead, their work pointed to a pressurized geothermal reservoir located at depths between 2 and 4 kilometers.
Laboratory experiments using rocks collected from the caldera showed how a fibrous cap rock seals the reservoir, trapping water and vapor until pressure builds high enough to fracture the overlying crust. Rainfall recharges the reservoir over time, slowly raising fluid pressure. When the cap rock seals completely, the system becomes a closed pressure cooker. The study suggested that managing groundwater flow, either by channeling runoff away from the caldera or withdrawing fluids from wells, could reduce pressure and prevent future crises. Not all scientists agree. Some maintain that magma or its gases still play a role. The debate continues. This was only the first warning. Civil protection authorities raised the alert level to yellow in 2012, a status that has remained unchanged for over a decade. Yellow indicates significant volcanic unrest requiring enhanced monitoring and preparedness. The Vesuvius Observatory operates a dense network of seismic stations, GPS sensors, gas analyzers, and thermal cameras across the caldera. But gaps remain. In early 2024, several monitoring stations near Solfatara went offline for weeks due to geothermal damage and budget constraints. During those outages, critical data were lost during periods of rapid change. Repairs are expensive and slow. Roads fracture faster than crews can patch them. Every time workers seal a new steam vent, another opens nearby. Local officials describe their efforts as volcanic whack-a-mole, a futile game where the volcano always has the next move. Evacuation plans exist on paper, but the logistics are daunting. Moving 500,000 people from the red zone within hours or days would require coordination across multiple municipalities, transportation networks, and emergency services. Traffic jams, panic, and infrastructure failures could turn an organized evacuation into chaos. The real danger may be something few people understand. Phreatic explosions can occur with almost no precursor signals. Unlike magmatic eruptions, which often involve detectable changes in gas composition, increased seismicity, and accelerated ground deformation over days or weeks, phreatic events can erupt suddenly when pressurized fluids encounter a weak point in the rock. The explosion fragments the overlying material, sending ballistic blocks and superheated mud in all directions. Ashfall from phreatic blasts is localized but dangerous, capable of disrupting infrastructure and contaminating water supplies. Landslides and sinkholes can form in unstable hydrothermal zones. The explosive nature of steam expansion creates shock waves that damage structures even without direct impact. At Campi Flegrei, the areas most vulnerable to such events would likely include Solfatara and Pisciarelli, where the hydrothermal system is most active and where historical evidence points to past phreatic activity. But the caldera has multiple weak points. Fractures extend beneath residential neighborhoods. Based on what researchers understand about the pressurized reservoir and fractured cap rock, a phreatic explosion in a populated zone could unfold with devastating speed. But no one saw what was building beneath the surface.
Seismic tomography reveals a complex subsurface structure. Below 2 kilometers, imaging studies indicate a gas-rich reservoir sits within fractured volcanic rock. Above it, between 1 and 2 kilometers depth, lies a deformed cap rock that has been altered by decades of hydrothermal activity. Beneath 3.5 kilometers, the basement rock of the Apennine nappes provides a more stable foundation, but within the caldera itself, the crust is fractured and permeable. Earthquakes migrate downward through the cap rock, some reaching depths of 4 kilometers. The most energetic events cluster along boundary faults that ring the inner caldera, structures that appear to focus stress and amplify seismic energy. Poor fluid pressure drives much of this activity based on current models. As fluids migrate through fractures, they alter stress conditions along faults, triggering earthquakes when thresholds are exceeded. The system is nonlinear and difficult to model. Small changes in pressure can have outsized effects. A single fracture opening in a critical location could potentially initiate a cascade of failures. And the forces beneath were still gathering strength. The Campi Flegrei caldera remains at yellow alert status. Nearly 3 million people live within the greater Naples area, with more than 500,000 directly above the caldera in the red zone. Ground uplift has reached 140 centimeters since 2005, with current rates accelerating to 3 centimeters per month in some areas. Burst-like seismic swarms linked to hydrothermal activity and potential phreatic explosions have increased in frequency since 2021. The Pisciarelli fumarolic field records temperatures above 140 degrees Celsius with carbon dioxide emissions exceeding 4,000 tons per day. Observations from the Bay of Naples, including localized algae blooms and reports of warmer waters, suggest the possibility of increased geothermal heat flow reaching the seafloor, though this connection remains under investigation. Research published in 2025 attributes much of the unrest to a pressurized geothermal reservoir at 2 to 4 kilometers depth, challenging earlier theories that emphasized magma ascent. However, scientific debate continues. Some researchers maintain that shallow magma or its gases still contribute to the observed phenomena. Others focus on the self-sealing caprock and its role in pressure accumulation. What remains unknown is when the system will reach its breaking point. Scientists cannot predict whether the current unrest will lead to an eruption, a phreatic explosion, or a gradual return to baseline activity. The caldera has experienced multiple episodes of uplift and subsidence over centuries, some ending without eruption, others culminating in violent events. Monitoring technology has improved, but fundamental uncertainties persist. How much pressure can the caprock withstand before fracturing? Will groundwater recharge continue at current rates, or will it slow? Can engineered interventions reduce pressure without triggering unintended consequences? The answers will determine the fate of millions. For now, the ground continues to rise, the sea continues to warm, and the steam continues to escape from vents that multiply faster than they can be mapped. Campi Flegrei breathes, and with each breath, the question grows louder. Is this the calm before the storm, or is the storm already here, invisible beneath our feet, waiting for the moment when pressure and fracture align?